So the other thing that I want to revisit, now that you have a better idea of aberrations in general, is the ray intercept curve. So what were we plotting on this labelless curve again? Plotting tan u, that is the tangent the ray made with respect to the optical axis, versus the error. Right? Now let's say I had some optical system, that's the optical axis, and I have a set of rays that are coming in, and let's say the system has been optimized so that they all focus at one point. If, and let me just draw these onward. Okay, this is very bad drawing. These are all focused at this point. Okay, that's a point. If my image plane were here and I was drawing the ray intercept curve for this plane, the rays at this plane, all the rays have come to focus at the same point, what would the curve look like? Straight line, but not a vertical straight line, a horizontal straight line, because the error is the same, is 0, in fact, in this case, right? So it's a horizontal straight line. They all have the same value over here, right? So it doesn't matter. So if this is tan u, they all have the same height. It's constant. Okay. Now I don't change anything in my optical system, but I move the plane that I am looking at. So instead of looking at the plane where all these rays are focused, I move my plane to this position. What will change now? Take the tan u, and for a particular, and how do we, again, you don't even have to guess which ray to start with. You start always with the topmost ray. The topmost ray's height or deviation from focal position is plotted on the rightmost of the curve. And then do it for the next ray, and then do it for the next ray. What do you get? So in this case, for graph 1, which is here, this is the topmost ray. This is the topmost ray, and it landed up here. And let's say I'm measuring heights from this point. So this height is h1. So it has, this is the angle. It makes a very small angle with the optical axis. So let's say maybe this is tan u for that. I'll call this, so this is h1, right? So this height is h1, and this is tan, let's call this u1. So this is tan u1. Then I would take the next ray, that's this ray. Now it lands up at the same height. So its height is also going to be h1, but its angle is u2. So I have the tan u of this angle, but it has the same height, right? So I'll do that for every single ray, and in this case, since they all come to focus at the same point, they all have the same height, but of course the tan u is going to be different in each case. So I'm just marking the angles here, but it's the tan of these angles. That's how I got this curve, this straight line. Now I'm saying plot the same thing, repeat this operation at the second plane. So let's start again. Okay. Now let's take the first ray. So this is the first ray. Oh, I didn't want to delete that, sorry. That's the first ray. So this is its height. Now this is slightly different from h1. right? Because it's at a further plane. Travel through free space changes the optical parameters. There's no change in angle, but there is a change in height. So the second graph that I plot, actually I am going to plot for exactly the same U1, U2, U3, because I'm taking the same rays, their angles haven't changed. But what has changed is their height at this plane. So let's consider this first ray. This is his height, H1, and let's call this L1 to show we are at a different plane. So L1, which is slightly bigger than H1, because the ray has traveled like this. So if this was H1 position, L1 is going to be over here. Then I take the second ray. This is the second ray. This is its height. This is L2. Now you see a big difference between, you just shifted the plane that you're looking at. At this plane, it didn't matter which ray you took. All the rays had the same height. But when you moved plane, the rays no longer have the same height. So you know that you will not have a horizontal line. Right? So you don't have a horizontal line. So this is L2, which is slightly larger, so it's over here. If I take the next ray, this is its height, so I'm going to have this. And so it turns out you will get a straight line. It's not a curve. It's not a, there's no reason for it to bend again. The rays just go on increasing in height. Right? A meniscus or something like that would mean there was again a reduction in height. There's nothing here to cause a reduction in height. So I do again get a straight line, but the straight line will now be rotated. So defocus, what have you done by moving your image plane from this plane P1 to this plane P2? What have you done? You have defocused. P1 was the plane where the best focus happened, but instead of looking at P1, you looked at a different plane. And what did that do to the RIC curve? It just rotated the RIC curve. So defocus rotates the RIC curve. So if you understand the RIC curves really well, if you're given a set of RIC curves for an optical system, you don't know anything about the optical system, but you're given these curves, you will be able to look at this and get a sense of what this system is doing, where you're looking at the system, has there been some correction in the system. So for example, what did our RIC curve look like for a system with predominantly spherical aberration present? It was something like this, right? I mean, I'm not drawn it very well, but something with anti-symmetry to it, right? So if you had a system like this, you would say there's predominantly spherical aberration present. Now, if I gave you, I said I'm going to change something in this system, and the changed one looks like this. What do you think has happened to this system? What would you say is the aberration of this system? It has anti-symmetry. So what is the predominant aberration? Anti-symmetry. It's still spherical aberration, but it doesn't look like our typical spherical aberration. What happened in spherical aberration, or what is spherical aberration? The further you go away from the optical axis, the worse the aberration gets. And that's why this goes on increasing like this and this goes on increasing like this. If I increase the aperture of my system, I would go on having this get larger and larger, because the further we went away. But what is the graph below showing you? The further you're going away, it's getting worse. And then what happens? So what does that give you an idea of? So this is a system with spherical aberration corrected. It should have been going like this, but something has been done to this system that pulls it back down. Not all, if there was no aberration, if I had got rid of all of the spherical aberration, my RIC curve would be a nice flat horizontal line. But I said, and I said it repeatedly, you never correct for all zones of the lens. So this shows you some zones are corrected for. And why is this still better than this case? Because here the central part is fairly corrected, and as you go further and further away, it gets worse, and at least that region gets corrected. The place where it would have got worse is corrected. So even though it's not corrected here, that is not the zone where it's the worst. And that's why sometimes this is an adequate enough correction, because it doesn't allow the aberration to increase too much. It pulls it back down when it's getting too large. Okay? Right? I've just given you here some examples of what the aberration curve looks like for some of the monochromatic, and earlier we've looked at some of the chromatic aberrations. So understand the curves we plot. These are transverse curves. We plot transverse curves, we plot longitudinal curves, we plot longitudinal curves which are focal distance versus height, we plot longitudinal curves which are focal distance versus wavelength, we plot transverse curves which are tan u versus error, transverse error. So you have to understand what is being plotted in each of these curves, what the curve looks like when there is one aberration predominant in the system, how correcting that aberration will change that curve. Okay? And finally, in a real system, you will have all the monochromatic aberrations as well as chromatic aberration present simultaneously. So the curve is the combined effect of all of those, and of course that makes them harder to analyze. But if you don't understand them when their aberrations are present independently, there's no way you're going to be able to analyze the curve when the aberrations are present together. Okay? So to understand why diffractive optics has a different dispersion, you have to understand how diffractive optics works. In refractive optics, this is not part of this course, but since you have asked, let's take a lens. Okay, this is a standard plano-convex lens. Now, in the ray optics picture, we don't really worry about what's happening to the wave. But if you really want to understand why does this focus? If I look at the wave that's incident on this lens, the wave front of this wave is, say, coming in like this. Now, what does the ray that goes through this travels through the longest path. So, it has slowed down the most. The ray that goes through this region, it's already in air while this is still traveling over here. So, it's in air and it's traveling faster. This is traveling through glass and it's traveling slower. So the wave is going to, actually, oh my God, the wave is not doing anything of the kind, okay? It has a nice spherical shape and it's going to go on reducing till it goes to the origin of the, okay? Now, why has this happened? Because the wave travels through this region. So everywhere there's a different thickness, but now you know it's not just the thickness that matters, it's n into L that matters. So everywhere this part of the wave has traveled through some NL1, this part has traveled through NL2, this has traveled to NL3 and so on. And that is what changes the shape of the wave. This actually relates to phase. Right? You need to go back to, so if you really want to understand, in geometric optics, we don't try to understand why things happen the way they do. It is empirical. It's based on, I've seen this happens, it works. Right? But if I really want to understand, I have to go back to wave optics. And in wave optics, you know that the moment you write down the equation of a wave, you are going to write out in terms of an amplitude and exponential j phi, a phase. And this phase is nothing but 2 pi by lambda into the optical path length. So if this is phase, if I said, okay, let me add plus 2 pi everywhere, doesn't make any difference. So I can convert this lens into a lens which just has these variations. I've removed all the excess 2 pi's. But in doing that, when I say 2 pi relates to a distance of lambda. This becomes an extremely dispersive element. Diffractive optics is horribly dispersive because I design it for one wavelength alone. And its dispersive nature is opposite to that because the way it's working is quite different. Okay. So combination, so you have these telephoto lenses from Zeiss, the kind that you see on photographers use for sports photography and so on. So the zoom lens is so long. So there's so many refractive elements in there. You can add up the chromatic aberration. It can be really, it wouldn't be useful unless you did some serious correction. So you can have a range of refractive elements and one diffractive element to correct for that, and the diffractive is thin and slim, so it's a very lightweight element that can do the correction. Okay.